Hello everyone, in this video I'm going to show you another theorem about integrating functions with discontinuities. And so basically in this video only contains one theorem, and I'm going to show you the proof of the theorem. And in the next video probably I will give you some, we're going to continue to see some properties of integrals, right? Okay, so let's get started. The theorem says assume f from ab to r is a bounded function, and let's we take a point C in ab. Then f is integrable on ab, the whole interval, if and only if f is integrable on ac and cb at the same time. In this case, we will have that the integral of f on AB is equal to the integral of f on AC and CB. Right, the proof is not difficult. It's all about taking some partitions. So, to prove it's integrable, basically you want to show that you want to find some partition that satisfies certain criteria, right? And so the point is, how are you gonna choose the partition to show it's integrable? Okay, now first of all, let's suppose f is integrable on AB. Suppose f is integrable on AB, and then what information can we get from the integrability of f on AB? We know that for any epsilon larger than 0, there will be a partition P on AB, such that the upper sum of f with respect to P minus the lower sum will be smaller than epsilon, right? This is the definition of integrability of f. And so we want to show that f is also integrable on AC and CB, and actually it's the same to show that f is integrable and on AC and CB. So basically we only show that f is integrable on AC, and it's completely the same thing to show that it's integrable on CB. Okay, so I've said it before, the main point of the proof is to find a suitable partition, right? And what we only have actually is the partition of f on AB, the whole interval, right? And now we want to show that f is integrable on AC, this subinterval. So one thing I think we all should come up with is that we can maybe take, say the partition on AC, we call it P1. We can take the intersection of P and AC, right? But you have to make sure that the point C is also included in this partition P1, right? Because this is how we define a partition. So maybe you wanna union a single point C, but the point is, actually here we don't directly take union of this part and the single point C. Instead, we first give PC a partition of P on AB. Let the partition PC to be the union of F and C, and I'll explain why we don't use the previous method I just explained. Okay, so then let P1 to be the intersection of PC and AC, A to C, this subinterval. And now everything's done because everything's prepared. Because well, C is also included in the partition P1, right? And similarly, you can take P2 to be PC intersects CB, right? It's the same thing. Okay, so now after we take this partition, we will have UFP1 minus LFP1. This is the upper and lower sum of F on AC, right? This part will be smaller than UFPC minus LFPC, right? Because P1 is actually the subset of PC, right? And this part will continue to write this, and the quality we will get UFPC minus LFPC is going to be smaller than UFP minus LFP, right? Right, because PC is a refinement of P, right? So, and we know that this part is smaller than epsilon. So finally we get UFP1 minus LFP1 is smaller than epsilon for any epsilon larger than 0, right? So we show that F is actually integrable on AC. And why we don't choose like P1 to be this part union the single point C is that if you choose it like this way, so that means we don't have we don't have the partition PC. So in this case, you cannot actually directly say that UFP1 minus LFP1 is smaller than UFP minus LFP, because you don't know actually if C is included in the partition P. So this is why we are trying to get help from PC, the partition which is a refinement of P, union where you're taking the union of P and the single point C, right? Okay, so right, and now we already proved that if F is integrable on AB, then F is integrable on AC and CB, right? And on the other way around, we want to show that if F is integrable on both AC and CB, then F is actually integrable on the whole set, on the whole interval AB. Right, okay, so it's actually pretty similar. So suppose F is now integrable on both AC and CB. So what we will have that for any epsilon larger than 0, there exist partitions P1 and P2. On AC and CB respectively. CB, sorry. And by the definition, we will have UFP1 minus LFP1 is smaller than half of epsilon. This is a classic trick we always do, right? Take the half of epsilon so that at the end the result will be a nice and clean epsilon. But if you don't actually know what will happen in the next step, it doesn't matter, you just choose like epsilon, and the result, and at the end you might get something smaller than 2 times epsilon or like 3-4 times epsilon, and that doesn't matter. You just if you want to change it to be to let the proof to be like clean and to be clean and like more like prettier, you can change it at every step from backwards. Okay, so u of p1 minus a of p1 smaller than half epsilon, and u of p2 minus a of p2 is also smaller than half epsilon, right? And so that now we take the partition on AB. P is a partition on AB, right? And how we're going to choose P? It's very clear that we can choose P to be the union of P1 and P2. Check the endpoints A and B are both inside the partition A as partition P on AB. So we don't need to add other points to it. So we will then have U of P minus L of P equal to what? Well, consider P to be the union. Consider P is now the union of P1 and P2. We will have U of P minus L of P to be U of P1 minus, actually we can first write U of P1 plus U of P2 minus L of P1 plus L of P2, right? By the definition of P. And then combine these two together, we have U of P1 minus L of P1 plus U of P2 minus L of P2, right? So that is going to be smaller than epsilon over 2 plus epsilon over 2, which is equal to epsilon. A nice proof, and we're done. Right, so then f is integrable on the whole interval AB. Okay, so the next thing we want to show is that we have the integral of f. Want to show the integral of f on AB is equal to the integral of f on AC plus CB. Right, so the way we show it is actually we first show this part is smaller or equal to this part. To the left hand side is smaller or equal to right hand side, and the left hand side is also larger or equal to the right hand side. So then the left hand side must be equal to the right hand side. Okay, so this is how I'm gonna show it. So, well, by the definition of the integral of f on AB is equal to the upper integral of f, right? Upper integral of f. Since f is already integrable, the integral of f on AB is equal to the upper integral and also the lower integral, right? And this is going to be smaller than U of P, right? The upper integral is kind of like the limit of U of P, the limit of upper sum. If you take a finer and finer partition, and U of P is gonna be smaller than L of P plus epsilon, right? This is the definition. This is the property of the upper and lower sum. U of P minus L of P is smaller than epsilon, or the definition of integrability, right? Well then, L of P plus epsilon is actually equal to L of P1 plus L of P2 plus epsilon, right? Because P is the union of P1 and P2. And if we go further, we will see that LFP1 is smaller than what? The integral of f on AC, right? And LFP2 is smaller than the integral of f on CB. So we show that the integral f on AB is smaller or equal to the integral of f on AC and CB. We have also a epsilon, but it doesn't matter if you take it away, right? Because epsilon can be extremely small. Okay, and so the next step is that we want to show that this part is larger or equal to the right hand side. And well, the tricky thing is that here we don't actually show that left hand side is larger than right hand side. Well, it's actually the equivalent thing, but we actually show that the right hand side is smaller or equal to left hand side. It's actually the same, it's just well, you can see plus the integral of f on AC and CB is gonna smaller than UFP1 plus UFP2, which is smaller than RFP1 plus RFP2 plus epsilon, right? Because this part minus this part is gonna be smaller than half epsilon, right? So 2 times half epsilon is epsilon, right? So then continue this way, we will have equal to RFP1 plus RFP2 is going to be equal to RFP. And don't forget plus epsilon, which is smaller than the integral of f on AB plus epsilon. Doesn't matter, because epsilon can be extremely small as like almost small, like as small as 0. Okay, so we prove that both sides, the left hand side is smaller or equal to the right hand side, and the left hand side is also larger or equal to the right hand side. So we will have that actually the left hand side is equal to the right hand side, right? So the integral of f on AB is gonna be equal to the integral of f on AC and CB, provided that f is integrable on AB, on AC, and on CB. Okay, so this is all about the theorem and its proof. It's all what I want to say in this video. So, well, I hope you enjoy it, and see you in next one.